working as a junior resident in NIMS Patna.
Okay, so thank you so much. So we will now start our workshop, and that is on the survival analysis. So survival analysis is a topic where you may need some of your earlier concepts also, like the basics of, because we are learning the survival analysis over JAMOVI. Many of you probably must have done this on SPSS or any other software. So how we will go? So with the few theoretical introduction of the topic and the concepts, then we'll go to the JAMOVI and see how there are various ways of doing the survival analysis and how we can do it over JAMOVI. And the reference which we have followed for making the content, most of the reference is from this book, which is the Survival Analysis by Klinbaum and Michael Klin. The same reference book, I think Klinbaum has written the book on logistic regression also. So that also, I think, with the our earlier workshop, we have followed the book by the Klinbaum, because it's a less of mathematics. Because if you see the survival, a lot of mathematical concepts is involved. But probably this we found that less of mathematical concept as compared to any other textbook. And then we have referred to the Leon Goddess and few other books also for making the content of this workshop. So the objective of this this is a workshop. So the objective of this workshop to understand the basic concepts of this time to event data, because we'll see what is this time to event concept and time to event outcome. And we should be able, at the end of this session, we should be able to construct a life table and interpret, basically, because construction is like, it's the software job, but the interpretation, it is you who is going to interpret. So you should be able to interpret and understand the background statistics, which is involved in the construction of this life table and the survival plot using the actuarial approach. And then we should be able to construct this survival table. We should not be saying it as a life table, rather it is the survival table and survival plot using the Kaplan-Meier approach. We will also see how to compare the two survival curves using log rank or any other. There are many other tests also for testing the test of significance. And then we'll see, when you have to go for a modeling, how you can apply that Cox proportional hazard model and how you can interpret a hazard ratio. And we'll also see various other factors involved, the assumptions in the Cox proportional hazard. So basically, these three approaches we learn: the life table, the Kaplan-Meier, and the Cox proportional hazard, the univariate as well as the multivariate. So starting from this, because we generally go from known to unknown. So I assume that all of you now know what is a logistic regression, how do we model our data using logistic or linear regression, because that is again one way of modeling your data and to do some prediction. So how this time to event analysis or time to event data is different from those data where we don't consider this time, because the difference here is the time, when that particular event happened. So suppose this is first situation. You can see here there are two situations. So you have followed a set of 20 males. This is a set of 20 males, and you have followed them up for some period of time, and you have seen that approximately 8. Just a sec. Let me read this. So you can see here that this 8 people, they are followed up for some time, and ultimately at the end of this follow-up time, the 8 out of 20 developed the first MI, that is the myocardial infarction. Then again, second, this thing is like set of 20 females. Again, after some time period, we have followed them up also. And again, they have developed, like 8 female out of 20 developed the second MI after the first MI. So this is both, the end point is the development of second MI after the first MI. And we are following them up. So can we say that the risk, if I have to calculate the risk, the risk will be same in both the individual, because the risk will be 8 will be the total number of cases. The 20 is the denominator, and we will multiply it by 100, saying that the risk of the second MI after the first MI is 40% in both male and female. So can we say that if we are only recording the outcome? Here we are only saying that the event has happened or not happened, and we can say that the risk is same in both the group. Now, if I show you this, where there is a time, but in this, if I divide this time in 3 quarters, let's say the first quarter, first like three time period, first third, the middle third, and the last third, then you can see here that in case of a male, more number of men, they are developing the second MI immediately after the first MI, whereas in case of female, they are developing the second MI after the first MI, basically in the last, during towards the end of the time period. So final risk is same in both these men and women, because you have seen that it was 40% in both. But can we say something like, from this, are we getting some additional information from this slide? And what is that? So again, the same thing, like the men, they are developing the second attack soon after the first attack, whereas the women, they are developing quite later, the second attack of MI after the first attack. Because here I was having my time to event analysis. That means I was having this time until that event occurred. That's why I can say that the difference of these two people, the experience of having second MI, there is a difference in the male and female. Whereas in the previous example, I will have to say that both are exactly the same. So can I still say that the male and female, they have a similar experience of second MI? So the answer will be no. So that's the beauty of a time to event data, because ultimately you can say that event happened in both the cases, but the speed of occurrence of that event and time when it happened, that idea you will get by analyzing such data. Because this is also important, why the survival analysis or time to event data is important, because many cases for policy making also you need such type of analysis. And again, if the patient asks from you regarding the prognosis, whether it is the recurrence of second MI or any other prognosis, we'll see, you need to tell him this, like what will be the risk, or how much time may happen, like when he or she will have a second attack of MI. So based on these survival analysis, you can define the prognosis also if the patient asks you. Again, this is one example which I have taken from the Leon goddess. So here you can see that he is also explaining the same thing, that there is two hypothetical population. There is a survival curve A and survival curve B. So if you say that the final outcome, the 5-year survival, that is same in both the cases, because both these, the survival decreased to 10%. If you see this 10% value, in both the cases, they are reaching to the same point. But the survival experience of the person who are here in the curve A is different from the survival experience of the person who are here in the survival curve B. Because I will explain what are these survival curve, but just to explain why these time to event data is important. Because if you just see the last outcome, then, and if you if you don't see anything in the middle, then you may miss something very important. So here the survival experience of people of the survival curve A, that is definitely better, because if you see this 3-year, then by the end of 3 year, the survival probability of this curve B, it is 30%, because it is like if you see on the y-axis, it is the percentage of surviving, and if you see the x-axis, it is the year of study. So in case of B, by the first year, the survival probability decreased to, let's say, it is 30%. But in case of the hypothetical population A, even by the end of 3 year, the survival probability is as high as 90%. So this is the beauty of time to event data. And if you have the exact survival probability, you can calculate the overall or the cumulative survival. So in nutshell, we say that when the research question is only required to analyze the outcome of interest, then in that case we use the logistic regression. But when we have time also, like time until that event happened, which is known as the time to event data, then we use some a type of analysis which is the survival analysis. So now, since we have introduced this term, what is the time to event data? So there are two concepts in time to event data. There's a time and there is an event. So now, what is a survival analysis? So basically it is a branch of statistics which analyze the time until the event of occurrence. So please focus on this word, which is until. So time until that occurrence of event, that is known as the survival time. And this whole exercise, this whole activity is known as the time to event analysis, where I have got two things. I have got a particular variable, which is the time variable, and the second variable, I have got that event. A particular event happened or not happened, or how much time it took to how much time until that event occurred. So remember this term until. So we always explain the survival time. How much time until that second MI? How much time until the death? Now coming to the second concept, that is either you can measure the start time and the end time. So in the variable we'll see in the data, you can have the total. Okay, is my voice breaking? I think Priyanka is writing. Can someone confirm regarding? Then I'll try to do some changes in my setting.
No,
Keep
ma'am.
saying
Ma'am, it's
no.
clear, ma'am.
Okay. So Priyanka, you can check from your end. Probably sometimes if like the connectivity at your end is low, then you can again rejoin because the other people are saying it is fine. So now coming to this start time and the end time. So in any variable, you can measure it in the form of a start time and an end time. End time means when that event occurred. Or you may have a total time that we'll see in the data. So survival analysis is again done for this such type of time to event data when you have got a start time and then you have got something known as the event. Coming to the unit of time. So it is very important for you to mention in your protocol or in your analysis what is a unit of time. So that unit of time can be in seconds when you are like doing a resuscitation over the baby. It can be a time in second, or it can be a time in days. It can be a time in month or week or year or whatever. So that you have to specify, like in what unit you are measuring the time. And the event, it generally survival analysis was invented when the event was negative. That means it, related to death. But again, that event can be a recovery, the event can be a relapse, or the event can be a disease, development of a disease also. So again, for any survival data, it will have a start time and it will have a end time. Start time means when that individual got recruited in your study, then you follow that individual up to a particular time when that event happened. And that duration of event can be in the form of a second, minutes, hours, days, months, or years. So instead of simply asking, did the event happen? Survival analysis, it asks how long until that event happens. Okay, so that remember we have emphasized that term until. So remember that until because it will help you to understand the difference between hazard and the survival. So that's why whenever we call survival, we say that this is time until that event happened. So there are some key terms in this survival analysis, and we'll explain these terms one by one. So there's the first term which is known as the survival time. So this survival time is again, like I said, the proportion of people who have survived past certain event. So the time duration from the start of event until that event occurred, that is known as the survival time. And then what is because it is time to event, so there will be time which is known as the survival time, and there is an event. An event is always known as the failure, even if it is a recovery. But traditionally, we call it as a failure. That's why the term hazard is there. That means even like you have done some surgery and you are measuring that in how many days or months the person will be ambulatory if it is a knee replacement surgery. So it is a positive outcome, but still we will call that as a failure or as a hazard because that's how the terminology has been developed. So don't confuse this survival always with negative outcome. If outcome can be negative or positive, just remember event. The event can be a positive event or it can be a negative event. The positive event can be like recovery from a disease, ambulation from a surgery, or resuscitated neonate after the effort of resuscitation. Or it can be negative, like development of a disease, development of a relapse, or death. So this is the event. So the outcome of interest, that outcome of interest can be positive and can be negative. There are other terms also like censoring, survival, and hazard function. I will be explaining these terms at the respective point. So right now I'm holding myself of explaining these terms because at appropriate place they will come. So coming to survival time, again, like I said, this is the duration of time from a defined start point to the occurrence of a specified event. And we measure this survival time for each individual. And if the event has not happened, then we call that as a censored. And censor is, that means that that person outcome is not there with us, but that time is there. And we'll explain what is censoring again in detail. For example, if it is a medical study and if I am following up a patient from the start of chemotherapy, and then my event of interest is relapse. So if the relapse happened in that particular female after 12 weeks, then I can say that her survival time is 12 weeks because I will say time until relapse. And time until relapse is 12 weeks. So the survival time is 12 weeks. Again, if it is a recidivism study, which is this example I have taken from Klimbaum because he has given this example also. So he is saying that it is done in case of other social sciences also, like rearrests of the parolees. So if the B is released and tracked and he is rearrested after 18 weeks, so his survival time is 18 weeks. So we will explain the survival, that means survival until the rearrest. So this is some example. The study group is of leukemia patient and the time to event event is like a remission. So leukemia patient event is remission. So I will say time until remission. Similarly, if I am following a cohort which is disease free and I am measuring the event of interest is the development of a heart disease. So I will say the time until heart disease. My group of population is an elderly 60 plus population and my event is death. So what will be my survival time? Or survival time is the time to event outcome. So my survival time will be time until death. And again, these are the units like we plant also time until death and I'm measuring it in months. So time, like I said, to conclude, all the time which we measure, that is the survival time. And what do I mean by survival time? Time until event. And what is the event? Event is always, we define the event as failure. But again, I'm repeating the same thing. Don't confuse that this failure is always negative. No, if your event is positive, then this failure is ultimately it is a positive outcome, but we define it like that. Okay. So event is failure and time is survival time. So please remember whatever time we are measuring, that is the survival time and how we say that time until that event. And the event is a failure. Whenever that event happens, that means that person has failed. So we call it failed or not failed. If failed, that means the event has happened. So again, we have got two types of this thing here. There's a survival time and there's a survival data. So survival time is for each event. We record the amount of time and this time is known as the patient survival time. And this whole set of such survival time is known as the survival data. Again, the same example, cancer patients where event is death, post-surgical patient where the event is surgical site infection. So if you see these are positive, these are negative event, death and surgical site infection. These are again all negative. HIV positive individual, progression to AIDS, stroke survivor, recurrent stroke, heart transplant, graft failure, and time frame is again time until diagnosis, or surgical site infection, time until surgery to infection, because you have got a start time also. And how do we define the start time? So basically, start time, you take the time of diagnosis. So whenever you have got the diagnosis, that is your start time. So that's why it is saying that time from HIV diagnosis to AIDS recurrence. So now there are a few questions. You have to identify the failure in the given research question. So my research question is, if you want to estimate the median survival time, or if you want to estimate the survival time for the termination of exclusive breastfeeding in population X. So in this case, who will be the study participant? Yes, all of you, please type in the chat box. Who will be the study participant? Dr. Lakshmi is saying lactating mothers, infant, lactating mother, breastfeeding women. So basically, yeah, true. It will be like that, the pair of mother and child. And what is the event? What is the event here in this case? An event, remember, event will always be failure. Yes. So event will be termination of exclusive breastfeeding. And what is the survival time? How you have to write, how you will write the survival time. So we write time until. Please add this word until. So time until the termination of exclusive breastfeeding. Because when you conduct, yeah, time until, remember this, because otherwise you will get confused, because in our PG seminars also we have seen that like generally PGs, they get confused over this survival. They always think that this is like always related to negative, so they try to make it opposite. So no, you have to define the event, and if the event is like in this case termination of exclusive breastfeeding, so your survival time will be time until event. So time until termination of exclusive feeding. You will just add these two with the term middle connecting word, which is the until. Okay. Now coming to another example, you want to estimate and compare the median survival time for blood pressure control in the two group, drug A and drug B. So who will be the study participants? So I'm just telling study participants will be hypertensive people. But again, what is a failure in this case? What is the event? How I have defined? So I have written survival time for blood pressure control. So my event is, yes, my event is hypertensive control. So it is a positive event. It is not a negative event. And survival time is time until the control of BP. Yes, time until control. We are not, Dr. Geeta, we are not writing reduction of BP. We will just add these two with the term until. So we will write time until the blood pressure control. Some more examples like the first MI episodes to relapse, the analyze the time for fracture to heal after the fracture. Then a study of coronary artery bypass surgery may analyze time from surgery until death. Or if I'm like doing some assessment of ointment application, so after the application of ointment, what is the time until that rash has cleared up? So while interpreting this survival result and graph, we should always see whether this event is negative or positive outcome. That will help you to understand and write your interpretation well. So now you have planned to conduct a survival analysis, and you are conducting this study where you have have this data of this time to event. So can you anticipate that what can happen in this case whenever you have this time to event? So in this case, will you be able to define everyone who has developed event or not? Let's say the same example of stopping the exclusive breastfeeding or cessation of exclusive breastfeeding. So if you are following women for this exclusive breastfeeding, and can you say like, and if your follow-up study is, let's say, for 6 months. So can you say that what problem you may encounter? So one problem you may encounter that you have come to that study end, but still there were many women who are still continuing with the breastfeeding. So there will be many people for whom the outcome or the event has not happened. Again, to reiterate the same thing, if this is a bottle and there are butterflies in that, and if I want to know what the average time a butterfly will survive in this, and if it is kept in a closed bottle, and I plan to observe the bottle for 30 days every day. So, can I get the answer like what will be the average time a butterfly will survive in this case? Yes, I can have because it is a closed container and the butterfly cannot like fly away. So I will have a precise time. But in any area, in any setting, that's an open setting. So that's the difference between the open setting and a closed setting. A closed setting like this, you can, or the people who do the experiments on animal, like the mice or guinea pigs, it's a closed setting. So they know like it is done under a closed box, so that particular animal can be observed. But in case of human being, it cannot be a closed setting. People are coming and going. So in that case, okay, this is the same. In that case, this is again the same butterfly example. I have tried to shown it with the time of start and the time of event happening. So if I start all the butterfly by observing on the 24th this September, and then the date of event for them are like different, and all the event they all are died because I can have the data of all the butterfly here because it is a closed system, and this is the time to event like 20 days for the first butterfly, that means time of death, the 15 days for the second, 18 days for the third, and so on. So there are variable time to event for all these butterflies because it's a closed system. So I have the data for all the butterflies. But if I open the bottle, then definitely there will be many flies which are either not died or they fly. So flight ones are like, or the not died, where even after the end of 10 days, I can see that the event has not happened. And such type of data where the flight or not flight, not died, that means the event has not happened. That event is known as the censored event. So remember, initially I have talked about this censoring. So censoring is a special type of data analytic technique in case of a survival analysis, because if you have to do a logistic regression or linear regression, there you will have to do the multiple imputation method to take care of these missing data. And again, if you don't have the event of interest, you generally you say that the event of interest does not happen, but you don't take care of that particular variable, that is time until that event. So this is a special type of the survival analysis technique, that even with the censored data, you don't want to lose that censored data because you have got some information up to some period of time. So that technique, using the analytical survival analytic technique, you take care of this censoring, and that makes this survival analysis a unique type of analysis because here you take care of the censored data and that is included in the analysis. Again, this is same example, like if I want to know the progress of a patient until the occurrence of some well-defined event, like event of second MI after the first MI. So there can be 1% when the event has occurred. There can be another person where there is a loss to follow-up, and there can be another person where event not occurred, but the person stayed till the end of duration. So I will say these two cases as event occurred, and these two cases as loss to follow up. These two cases, I will say that they are loss to follow up, means they are censored data. These two are the censored data. That means you don't have the outcome, whether it happened or not happened, but you have the time until that person was there with you. So how do we define censoring? So censoring is basically, for example, in this case, you can see that the study has started and the study ends here. In this, at this particular time period, the study ends and here. And but this is a leukemia patient, and your your event is remission. So time until remission. But this person, this was not here. The study ended before. So this is the example of censoring. So what is a censoring? So basically censoring is a phenomena where you have got some information about the individual survival time, but you don't know when the survival when that event happened exactly. So you don't have that exact time when that event happened. So this is again a statistical term which we describe to convey the process of having incomplete observation, where we don't have the exact survival time, and there are various reasons for this not having the complete observation. So we define based on these reasons of censoring. So maybe the exact survival time we don't have because the person whom initially he was there in our study, but there was a loss to follow up. And the second thing, like person is healthy, or depending on the positive and negative outcome, the patient was there with us, but till the end of the study, the event does not happen in that particular person. So coming to this is again a type of censoring. You can see these are the ABCD 6 people. This again, this example I have taken from the Klingbaum. They are the sixth individual. The first individual, he has followed up till 5 weeks and he has developed this outcome. The second individual followed up for 12 weeks, but the study ended at 12 weeks. Third individual, he followed up for 3.5 weeks, but he withdrew from the study. The fourth individual followed up for 8 weeks. The study ended. The fifth individual followed up for 6 weeks. He got lost. And then sixth individual followed up for 3.5 weeks and the event happened. So if I arrange this survival data in the form of like a table, then this is the first column will tell you about the person or the event. And you know that in any data set, each row is for one individual. And the same principle applies here also. Each row is for one individual. So these are various rows which you will see either in JAMOVI or in SPSS, whatever data analysis software you use. This is the survival time. So you have got one variable where you have got individual. We have got another variable which is the survival time. So what is survival time? How we have defined the survival time? Survival time is time until that event happened. So that event can be a censoring because here the study ended. So that's why we will call it as a 0. So how we define in the code? We arrange the data like whenever that event will happen, we call it as 1. And whenever the event did not happen because the person withdrew or the study ended, we call it as a 0. So that's how we have written the survival time. Survival time will be written for all the people, whether they have met with the event or not. And then you have defined two terms, failed or event happened and censored. So this first individual, since the event happened, so that is 1. And for the last individual, also the event happened, that's why it is 1. For rest of the people, all these 4, since the event did not happen, either there was a loss to follow up, the individual withdrew himself, or the study ended. So that's why all the cases are labeled as 0. So this is how you have to arrange the data. This is just an example when you have to enter the data in the column, because right now you are having a data set with you. But when you will perform your own analysis, you need to understand how you will enter the data. And this is one way of entering the data, where on the first column you have got the person. On the second column, I mean, this is with the only 3 column we are showing. There may be many other variables also, but that we are not showing. This is how you have. So there are 2, again, time to event, remember. So this is the survival time. So this second column is the survival time, which is the time until that event. And the event can be a failure. Failure means that event happened, or it can be censored when you don't have the exact information whether that event happened or not happened. So am I making sense to all of you up till this point? How we arrange the data and the introduction of few terms like what is survival time, what is event, what is failure, what is time to event data, how it is different from the linear or logistic regression, or how this censoring time is helping us in the analysis of the survival. So again, since you know now there is a censoring, so there is a censored time and there is a censored data. So censored time is the survival time of loss to follow-up cases or event-free cases at the end of the study. And this is referred as the censored time. And the set of such data is known as the censored data. So in the previous example, if you see, these from B to this is actually known as the censored time. Actually, we define this also as a survival data, but since all these cases are censored, so this is the censored time, and this is your survival time. But again, to include everyone, like time until that event, we call everything as a time to event. So this is the survival time and the survival data, censored time and the censored data. Now, since you know by this time, you know what is a censoring, we define three types of censoring. In most of the textbook, you will find that they have defined right and left censoring. But Klinbaum has also given this concept of interval censoring, which is not always used. Most commonly, we use the right censoring. So now what is this type of censoring? So coming to the right censoring, what is this right censoring? So in the previous example, if you see the example which we have just taken to calculate the survival time, for B and for D, the study ended here. And this C person withdrew and this E person has lost to follow. So this was all happening towards right of the follow-up time. So that's why it is known as the right censored. That's why the name is. But what is happening here? Here you can see that the observed survival time, it is less than the actual survival time. Why? Because actual survival will what? When that event happened. But whenever you measure something this time or this time, in this time that event has not happened. So whatever time you have, that is the observed survival time. Okay? Because that time you have observed. You don't know the actual survival time because till the time that person was there in with you, that event was not happened. So that's why the actual survival time will be more than the observed. Or in other way, you can say that the observed survival time will be less than the actual survival time. Am I making sense to all of you with the example of right censoring? Yes, Dr. Tanya, what question do you have?
Ma'am, suppose I am just following up a retrospective cohort study that the GDM patients, how long does it take to develop type 2 diabetes? So
Okay.
some patients I am following up for 7 years
Mm-hmm.
and they have developed diabetes after 5 years of having GDM. So
Mm-hmm.
what will be their survival time? Time to event is 5 years, but my follow-up time is 7 years.
Okay.
So
But they have, when they develop the event, your event of interest is the development of diabetes after GDM, right?
yes, ma'am.
Okay. So now let's break up the concept. Your event is development of diabetes. Okay. Your
Yes,
start point is time of diagnosis of GDM. So how
yes.
you will define the survival time? Time until diabetes mellitus development. So at 5 years, that lady has developed the diabetes. So her survival time will be 5 years. Even if you have followed up for 7 years, that
Okay, ma'am.
doesn't
Thank
make
you.
sense. Okay.
Oh,
Since,
thank you.
I mean, you will have the time to event data only till that event happened. Even, or if like something, this is for the one terminal event. Although I have not explained, but there is something known as the recurring event. Recurring event means like the patient in cancer remission. You give chemotherapy, the person becomes remission free. Again, he comes into the cancer stage. Again, then you give chemotherapy. Again, he becomes remission free. Again, he comes back with cancer. So, such type of event, or the myocardial infarction, there's a first attack, second attack. So, that is known as the recurring event. So, in case of the recurring event, the analysis is different. So, I am not explaining recurring event in all my these 3 days, 3 sessions of the workshop. We are only explaining currently the one event of interest. It is not more than one like recurring event. So in your case, Tanya, the time to event or the survival time will be time until the development of diabetes, which is 5 years.
Okay,
Okay,
ma'am. Thanks, ma'am.
my pleasure. So am I making sense to all of you up till this point? Like right up till right censoring. What is a right censoring? Why do we call it right censoring? And what happens to the actual survival time as compared to the observed survival time if the person is a right censored. So doctor, can you show me the chat? Like, okay, so yes, from everyone, Dr. Poonam, Dr. Ajay. So we will now go ahead. So this is the right censoring where the observed survival time is less than the actual survival time. Now coming to the left censoring. What is a left censoring? So basically in left censoring, what happens? See, whenever you diagnose some patient, if you just recall the natural history of disease, the diagnosis time is different for different individual. There are people who seek care very early and there are people who seek care very late. So, for example, if you take this time as a zero time, and if the person has come to you and you have done the HIV test, so here you don't know when that HIV actually happened because the disease might have happened sometime before this. So that's why in this case, your observed survival time will be again more than or equal to the true survival time. Because the observed survival time, whenever that person has come to you, this is your this is your observed survival time. You will observe this time. So, but it will be more than this because this might either he may have the exposure here or he may have exposure anywhere between this and this. So in this case, your observed survival will always be more than or equal to the true survival. Similarly, like if you have done some surgery, let's say hernia surgery, and there is a recurrence. So there might be a case that you have done the surgery and you are seeing the recurrence. So in that recurrence, if that person comes to you at 3 months, then the recurrence may have happened before that. So event have happened between 0 and T, but you don't know the exact time. This is known as the left censoring. But most of the time you see that in survival analysis, we talk of right censoring because left censoring, you assume you have a clear-cut diagnosis or you define a clear-cut start point which is very objective in measurement. And that's how you can reduce this left censoring. So this is the left censoring when the observed survival time, either it is more or equal to the true survival time. That means whenever the patient comes to you, then whatever you have seen, that is less than that. Then again, the coming to the interval censoring. So again, the classical example of interval censoring is the HIV. So you have done a testing at time T1 when he was negative, and again you have done the testing at time T2, and that at that time it is positive. So it incorporates both right and left censoring, and it is as a special case where the true survival time is known, but within a interval, within a T1 and T2. So this is known as the interval censoring. For academic purpose, we define this interval and left censoring. But generally, if you see the survival, most of the data, 90% you can say they will be right censored. That means either the event did not happen till the patient was there with you, or the person was lost to follow up, or the person withdrew. So that's the most common. So right censoring is the most common type of censoring whenever you do a time to event analysis. So now coming to another question, whenever you enroll a person, is it possible to enroll all the participants in a study at the same time point or even a short duration? Can you enroll like all individual can the start point or the starting point of the person will be same date? Is it possible? So it is very difficult, right? Because it depends like how you are recruiting. If it is a randomized control trial, definitely you are recruiting individual everyday basis. If it is a prospective observational study, because generally we do this survival analysis either in case of a randomized control trial, RCT, or in a prospective observational study. So even if it is a prospective observational study or even a retrospective, that means you can say cohort study or a longitudinal data. So for such type of data, you will see that the start point is different. It is not always the same. For example, in this case, you can see, so if the start point is not same, then how will you calculate the time point? Or how you will arrange the data? That we'll see in the JAMOVI. So this is again one hypothetical situation where just we want to show you the difference, what is a mean survival time and what is a median survival time. Because the analysis unit, in case of a survival analysis, we always express in terms of a median survival time. So again, these are the 5 cases, and I am following up these 5 MI cases to see the recurrence of the MI. So this first individual, he was followed up and he developed the MI at 10 weeks or month, I think months. Okay, so he developed MI because I have followed, if you see this, the unit is in month. So he developed MI in 10 month, the second person developed in 2 month, third person 4 month, fourth person 8 month, and fifth person 6 months. So in this 5 cases, I have enrolled on the same date, that is on the 1st Feb. And in all these cases, the event had happened. So if I have to calculate the mean survival time, so how will I calculate? I will just add up all these time to event data and I'll divide it by the number of observation, which will give me the mean survival time, or is the 6 months. Again, this is in case if you have got all the data with you, then it is very easy to calculate the survival mean or median survival time. But the problem happens if there is a censoring. That means if the second person there is a loss to follow up, or that data is not there with you, and that fourth person also there is a loss to follow up. So will you be counting these 2 and 8 months in the calculation of a survival time? So now, since you have enrolled the all cases as, they come, so they have a different duration of the study, and it is not necessary that event may have happened in all. So in the first case, if you just don't take this loss to follow up, so in first case, it will be like 6.6. And in the second case, it will be like 3.2 days. So what is the difference between the two? If you don't take care of the loss to follow up, then if you are adding this, taking denominator as a 5 or taking denominator as a 3, it will have an impact on the median survival time. So that's why you take this time to event, means in the numerator, because if you don't take it, then if you take only these 3 and don't take it as in the numerator, then there will be the difference in the survival time. And that we'll see in the live table also, that you take care of the censored data. That means you include the censored data. So this censorship, it causes analytical problem because we don't know the exact survival time. And that's why, we calculate the probability at each time. And we'll see how do we calculate this probability. So this censoring, this survival analysis takes care of this censoring, and it includes that in the analysis. So again, so to summarize this survival analysis, what is this survival analysis? This is a statistical method for studying the time to event data. That means there is an event. Event is always defined as a failure, and the survival time is the time until that event happened. And again, the survival time refers to a variable which measures the time from a particular start time to a particular end time. And this time to event, which type of data it is? This time to event, because it is a time. So it is a continuous data, because time to event will always be a continuous data. That means it will be measured in days or in seconds or in months, whatever is the unit. And it is always used as dependent variable, this time to event data. So now coming to, I think, few questions, which I have that slide. So now please answer this question. In survival analysis, the outcome variable is dichotomous. Yes, please answer true or false. So Priyanka is writing false and Ajay is writing true. Namrata is yes and Pratik is true. So see, the dependent variable, outcome variable, we have got two: event happened or not happened and the time to event. So the outcome variable is the time. So time is a which type of data? Is it a continuous variable or a dichotomous? Definitely the event. Because in time to event, there are two things. There is an event and there is a time. But the dependent variable in case of a survival analysis is the time. So the time to event is a which type of data? It is a Continuous data. It is not a dichotomous. Dichotomous is for the event. But if you see time to event, which is my outcome, this time to event will be my dependent variable, which is a continuous data. So it is false. Okay. So now coming to this question. For a given individual, the event occurs before the person is lost to follow up or withdraws from the study, then this person's survival time is censored. Is it true or false? Please read the statement carefully. For a given individual, if the event happened before the person is lost to follow up or withdraws from the study. Remember Dr. Tania's study. She has said now that event has happened at 5 years. So this person's survival time is censored. So true. This person's survival time is not censored. This is the true survival time. So this is false. Again, this is one question. Censored data are used in the analysis of survival data up to the time of interval of censorship. True or false? Yes. So Dr. Richie is right. Dr. Ajay, Dr. Priyanka is writing false. Priyanka, this is true. Why? Because censored data up till the time of censorship, that's the only time which you have. That's why we say if it is a right censoring, observed survival time will be less than the actual survival time. So you only use that data up till the interval of censorship. Okay, I have not explained the risk set, so that's why I will not ask this question now. We'll go to our presentation. So this I have explained. So now there are a few common type of survival studies. I have explained this. Like generally we do the survival studies in the clinical trials or the randomized control trial. You can do it in the prospective cohort study, or you can do it in the retrospective cohort. Like Tanya was saying that she is following up all the women who developed the gestational diabetes mellitus to the onset of the diabetes mellitus. So they basically these are the three types of research design where we use the time to event data or the survival analysis. So what are the features of the survival data? Again, this is just the repetition. One important thing is generally this time to variable data it's a very skewed data, because it can have like one year or 2 year, or it can have like many years. If you are measuring it in days also, there's a wide range in your data set. So generally it is skewed in nature. So that's why you will see that all those Kaplan, Meier and all, they are the non-parametric. So this time to event data is usually skewed, and that is the non-parametric. So that's why you will see that generally we take the median survival time. We don't calculate the mean survival time in case of this time to event data, because it is skewed in nature. And so this censorship, about that censorship, we have already discussed regarding the censorship time and censor data. Now coming to, remember in the beginning we have discussed like there are few terms which are important for you to understand. So we have discussed what is a survival time. We have discussed what is a event. Event is failure. We have also discussed what is a censorship or the censoring. Now next come two more important functions, which is the survival function and the hazard function. Now, these are more mathematical, so that's why I'm not explaining these in the mathematical terms. So just remember, wherever you see this ST, this is calculated using the function, there's a function and limit property of mathematics of numbers. So it is calculated based on that. But just remember that this ST is the survival function and this HT is the hazard function. So now what are the characteristics of this survival curve? So survival curve, we always say that they are non-increasing. Non-increasing means that they will always be down. Down means it is not necessary to the event, whatever event you describe, whether it is event is a positive one or a negative one, with time that will go down. That means they head downwards as t increases. And what is the other property of this survival function or the ST? At time 0. So if what is here? there is a x-axis and there is a y-axis. So on x-axis, you can see that it is time, and y-axis, it is the survival function. So the survival function at time t is 1. That means you start, then everyone is alive, or whatever, whenever you start, everyone is healthy, and then they develop the disease. So at time t, this survival function is 1. That means at the start of the study, no one has had the event. That means everyone is event free. And when the time becomes infinity, that means when the time passes, your event become 0. That means if you just see this as a death, means if the event is death, then it is easy to understand. If the event is death, then probably at the end of your study, if the study goes for infinite number of years, then virtually everyone who is there in your study, he or she will die. So ultimately the survival curve, it comes to 0. So that's the property of a survival curve. So whenever you see a survival curve, it will always be non-increasing, means it goes down. And as the time passes, this survival function, it decreases. And at time infinity, virtually everyone will come to 0. So that's the feature of a survival curve. Now there's another thing which is known as the hazard function. So remember, we have explained this term of event happening. So event, we call it as a failure. So whenever that event happened in some person, that is known as the failure. So what is a hazard function? So basically we define hazard function as the instantaneous potential. If you see this word instantaneous potential, that means, and again we call it as a instantaneous potential per unit time. So that's why you see that whenever the unit is like in t, in denominator it is t, then we call it as a rate. So that's why hazard function is also known as the hazard rate. Whereas survival, if you see, we will see later that that's a probability. So that's why survival value will range from 0 to 1 because it's a probability. Probability of surviving past time t. That's the survival function. But hazard is the rate. Because in denominator, how we defined hazard? That instantaneous potential per unit time for that event to occur, given that the individual has survived up till time t. So ST is not failing. If you see the survival and the hazard function, they are related to each other. If you see ST, you say that not failing. Why? Because the event has not occurred, and HT is the failing. That means the event has happened. So if you have got ST, that means if you have got survival function, you can calculate the hazard function and vice versa. They are linked to each other with a mathematical formula, but that mathematical formula involves the calculus, this thing like integration. So that's why even I am not very good at mathematics. So we don't understand in terms of like calculus formula. For us, it is only important to understand that this ST and HT are related to each other. And if you know ST, HT can be calculated or vice versa. It is calculated using software. We don't have to do it. And it is not like 1 minus ST. Remember, you will not say that if survival is this, then hazard will be 1 minus survival. No, they are not related to each other like this way. Okay, so there is a different mathematical function. But again, so hazard is again always called as a instantaneous potential. That means in a very small time, what is the instantaneous potential per unit time of that event to happen. That is known as the hazard function. Now there is a very important concept which is known as the risk set. For people, generally, if you see these concepts of risk set and hazard, that is, you don't have to calculate it. Actually, software does everything. Even it gives you a table where it gives you the risk set. So what is a risk set? So basically, risk set is the collection of individual who have survived at least time t. So if you see in this picture, in this image, so here there's some image again I have taken from Klinbaum. So this t is the time of the event. Okay. Time survival time. This T is the survival time. This MF is the event. And this QF is the censoring. That means at time T, there was time is 0, time, and there's no event, and there is no censor. And here we have started with 21 people. And this is one example, which is the event here was time until remission for leukemia patients. So this is for group 1. So here you can say that I have started with 21 people. So I can risk set at this particular time will be like 21% survived more than equal to 0 week. That means since there was no event and no censoring, and I have started with 21 people, I can say that 21% survived more than or equal to 0 week. Now at 6 weeks, if you see 3 event happened. That means 3 people went out of remission. And then time until remission means 3 people. Again, the leukemia happened and there was one person who was censored. Okay. But again, what will be the risk set here? So in case of risk set, you do not deduct these individual in this column. Why? Because we define risk set as at least 21 people were survived till time 6, because either the 3 people who went out of remission, they also went out of remission at 6 weeks. And there was one censored individual that was also there with us at 6 weeks. So here that more than that equal to sign, it is there for all these 4 people, and that more than sign is for rest of the people. So for 17 people. So that's why we say that for more than equal to, because for 6 weeks, if you take this equal to sign, who are the people who survived until remission? So 4 people survived, but that will be like equal to, and rest 17 will be like more than. That's why we say that risk set remains the same. More than equal to 6 weeks, that means 21 people. Now, if you come to the third time, which is the 7 week. Okay, so if you see the 7 week, there was one person who had this event and there was one person who got censored. So what will be the risk set at time 7? So at time 7, what you do? You basically, if I have to calculate the risk set at time 7 week, then what I will do? I will deduct these 2 from this original number. So from 21, I will deduct 3 plus 1, 4. So here it will be 17 people who have survived for more than equal to 7 weeks. Similarly, if I have to calculate the risk set at 10 weeks, so how much I will deduct from 21? Yes, either you can deduct from 21 or you can deduct from this number, the same, this column. So what will be the risk set at 10 weeks? Yes, although it is written here. So what you do basically, you do this, you remove all these numbers from the original number. So original was 21. So I have removed 3 plus 1 plus 1 plus 1. That means 4 plus 2, 6 individuals. So that's why 21 minus 6, it becomes 15. Or what I can do, 17 minus 2. So it becomes 15. So that's the risk set. Yes, Dr. Richie is right, 17 minus 2. And this example also I have taken from Klinbaum. So we will share the book if you want to read it. But again, this is the concept. In case of a survival, you should, again, these you don't need to calculate. The software gives you the table where it gives you the risk set and it gives you the cumulative probability also. But you should be able to understand what is happening in the background. That's why we are trying to explain this. So have you understood up till this point how we calculate the risk set? For example, you can see here also, like if he's the same thing, if he's calculating the risk set at this level at time 7, then he has deducted these 4 individuals. Similarly, if he is calculating the risk set at 13 weeks, then all these people he removed from 21. Or there's another way, like you can deduct just the one row above. So you can deduct 3 from this 15. This is also one way. If you deduct 3 from 15, the risk set will be 12. So this is how you calculate the risk set. Now coming, risk set means all the individual remaining after that particular, if they have survived, how many. So in the beginning of that particular interval, how many people were at risk of developing that event. And like if I go to another question. So this is one question. So if I write this question, that the risk set at 6 weeks is the set of individual whose survival times are less than or equal to 6 weeks. Is it true or is it false? Is it less than or equal to, or it is more than equal to? If I show you another. At a particular time point, at 6 weeks, if there are 21 persons are alive, then how do we define risk set? 21% survived more than equal to 6 weeks. It will not be. Yes, Dr. Ajay is right. How we define risk set? Risk set at a particular row. If this is the row and if this is the risk set, then at a particular time point, we say that the risk set is 21% survived more than equal to 6 weeks. That's the risk set. That means it is the collection of individuals who have survived at least to time t. That means each person has a survival time that is either TF or longer, regardless of whether the person has failed or is censored. Remember, we have explained like here, the 3 and 4. These 4 people have survived at least for 6 weeks and rest 17 have survived beyond 6 weeks. So that's how we define risk set. Okay, that means risk set at a particular time period is the collection of individuals who have survived either equal to that time point or more than that. So that's why if you see this question, this one, the other one, which I was asking, the risk set at 6 weeks is the set of individuals whose survival time are either equal to 6 weeks or more than 6 weeks. Okay, so it is false. So right. Again, let me see any other question related to risk set. Okay, so if this is a question, so you can take your time in answering this question and you can recall that image. I will again show that. If the risk set at 6 weeks consists of, you can write it down. Ideally we should have given it in the form of a table, but if the risk set at 6 weeks consists of 22 people, okay, and 4 persons fail and 3 persons are censored by 7th week. So on 7th week, if you see that 3 persons are censored and 4 persons are failed, then what will be the risk set at, then if I say that the risk set at 7 weeks consists of 18. So is it true or is it false? So they are saying by. So from 22, how much? If you say that the risk set at 6 weeks consisted of 22, that means 22 people survived for more than that. And if you say that the 4 persons failed and 3 persons are censored by 7th week, so for 7th week, what will be your risk set? So it is false. Yes, it will not be. It will be it will be again, if you see, it will be 3. Yes, you are right. So risk, because by 7, even if by 7 month these people failed and 3% censored, you will say that the risk set is like 18, it's 22 only. Why? Because at least till 7 weeks they were able to survive. Okay, now this survival curve will come later. So we have understood this risk set. Now coming to the data requirement of survival analysis. So this survival analysis, we have to define the event of interest. We should have start and end point, and there should be a selection of. So I think this we have done. Okay. So I think Dr. Shamshad is saying that we should have a break. So we are back. So Dr. Poonam has asked me to again explain that. So Dr. Poonam, remember, I'll again go back to that slide. This slide. Okay. So consider this as a same question. This one. So at 6 weeks, he is saying that at 6 weeks, here 21 is there, but in the question it is 22 people are there in the risk set. And by 7th week, 4 people developed the case, event, and there was 3 censorship. So what will be the risk set at 7th week? Okay, that information you have. So since you have got 22 here as a risk set, you don't have any information of this 6 weeks period. This information you don't have. That's why here also you will have 22. Why? Because you deduct the cases which have happened before that. And if you see the definition of risk set, that says that how many people could survive at least up till either at least up till 7 weeks or more than 7 weeks. So if you can see this question, here it is saying that by 7th week, 3% censored and 4 failed. So at least out of 22, all 22 survived up till 7 weeks. Why survived? Because we defined risk set as more than equal to. So up till 7th week, these 4 and 3, they also survived. Like survived means you define that at least till 7th week they were there with you. So that's why your risk set will be 22. That means in the same row, we don't deduct the number of event or sensor data from that risk set, from that total number of individual. We deduct from the upper row, not in the same row. So at 7th week, since this 4 and 3 has happened, so that's why we will not deduct any number from 22. And it will be, the risk set will be 22. I don't know whether Dr. Poonam, am I making myself clear to you?
Yes, ma'am. Yes, ma'am. Actually, I assumed that 4 per 6 week actually while reading.
Okay. That 6 weeks actually, in this question, he has not given any information about the number, whether how this 6 weeks is there, like any other, because if he has given like at 6 weeks, the risk set was 22, but there was 3 sensor and 1, then we could have like deducted that number from the risk set at 7. Since we don't have that information, we will assume that the risk set is same, because it is the 22 people who survived at least up till 7 or more than 7. So that's how we define risk set. Now coming to So again, survival analysis, they are suitable for studies in which we have a variable time to event analysis, a time to event or the follow-up time with us. And these methods were developed to prevent the underestimation or overestimation. There could be two things. Here it is written only underestimation. We'll show with one example, if you don't take censoring, how it, overestimates or underestimates the survival time. So I think this I am skipping because it's these calculations are not needed. I am only coming to this the type of survival analysis. So survival analysis or this time to event data, it can be done using three approaches. And the three approaches are the life table approach, the Kaplan-Meier survival approach, and the Cox proportional hazard approach. This I am only discussing in terms where the event is not a recurring event. For recurring event, there's an extended Cox and some different type of analysis is there. So now coming to the discussion of life table. So what is this life table? So basically this life table that is not very commonly used method of survival these days, but the survival data initially it started with the concept of life table. So what is this life table? Instead of this is basically the insurance people, they used to measure this survival using this life table, because here you don't have the exact time of event you don't have, but it is between these interval. So that fixed interval, generally it is this life table is calculated using some fixed interval because exact time of event you don't have. And in the calculation of life table, it is assumed that on average the study subjects were at risk for half of the interval. And that's why we will see that you deduct the half of the individual from that person who are at risk of the event. So again, therefore we calculate the number of people at risk during each interval and we subtract half of the withdrawal during that interval. So censored data, how we use? Here we take it, we divide the number of censored people by 2 because we assume, since we don't know their exact censorship, so we assume that they were for the half of the interval, they were on the risk. So that's why we deduct half from the denominator. So in this case, again, if we have to include the censoring in the survival analysis. So suppose in my study, if I have a total of 10 patients and I have followed them up for 5 months after receiving the treatment, and my event of interest is the treatment of failure and the time is measured in month. So this is one example. So this is again how this is calculated. This I am telling you how this survival probability is calculated. So in this example, you can see there are 10 people and this is the exact, this is not the interval, like this is the exact time to event. So in case of first person, the 1.5 months time to follow was 1.5 months and the event happened. So what will be your interpretation? You will say that he failed after 1.5 months. Again, the second person is like followed up for 2. It is censored at 2 months. So you will say that he has left the study after 2 months. Similarly, at 2.8, there will be event. At 3.5, there is a censoring. At 4, there is a event. There's a 4.2 again, there's an event. We call it as a failed. And then these 3 were event free at the end of the study. Okay, so this is one survival. So if I have to calculate the survival probability, so I am calculating the survival probability and there is something known as the cumulative probability if I include the censoring. So with this example, I want to show you if you don't include censoring and if you include censoring, what happens to the survival time. So this is survival time if you include censoring. So survival time is calculated only when the event happens. Okay, so if like I start with at 0 week and there's no event and there's no censoring, So and I started with 10 individual. Okay, so at risk people is the 10. So survival probability is 1. So, and this is the cumulative survival probability. So cumulative means you keep on multiplying. That's the cumulative probability. And we have defined the survival as a probability. Remember, the hazard is a rate because it's the instantaneous potential per unit time of developing the event. Hazard is a rate, but survival is a probability, survival time. Again, at 1.5 this week, the event happened. So we calculate the survival probability only when the event happened. So here, one event happened and there was no censoring. So there was one event and there was no censoring. And at risk will be 10 because remember, since here there was nothing, so I did not deduct anything here, and the same risk set has come here. Why? Because I can say here at least there are 10 people who could survive up till 1 point more than equal to 1.5 weeks. So how I will calculate the survival probability? So at risk will be 1 by 10. So survival probabilities will be like 1 minus 1 by 10. So it will be 0.9. And what will be your cumulative? So cumulative will be 1 multiplied by 0.9. So 0.9 will be your cumulative probability. At 2 weeks, there was a censoring. Okay. So if there is a censoring, and then what will be the risk set at 9? So risk set at 9 will be how we will do. We will deduct this one from 10. So it will be 9. But at censoring, we don't calculate the survival. So the survival, it will be the same probability which is here at here because survival, here we calculate the survival probability is calculated only when there is an event. So here, since there was no event, so for censoring, we don't calculate the survival probability is same, which you can see from the above. Again, in the fourth one at 2.8 weeks, there was an event. So if there was an event, now what will be the risk set at 8 weeks? What will be the risk set at 2.8? So how I will do? How this 8 has come? From 9, either you deduct 1 or from 10, you deduct these 2. In both cases, it will come 8. So risk set is 8. So how we will calculate survival probability? Your probability of event will be 1 by 8. So your survival probability will be 1 minus 1 by 8. It is 0.87 and your cumulative survival will be, you multiply this with this 0.9. So your cumulative survival is 0.9. Again, coming to the next one, which is at 4th, if at 3.5, there is no censoring, so survival probability is same, which you have seen here 0.78. Again, we calculate the probability at this event. And again, here we will take 6. Why? Because from 7, we will deduct this 1. So it will be 6 people. So survival probability will be 1 minus 1 by 6. This will be 0.83. So this is how, if you keep on doing it, your overall survival probability is 34. How you can say that? That 34%, or if you like make it as 35 or 34.9% of the people, they time until. So you can say if it is a death, so they survived until this 34% until the end of the study. So this will be your, and then if like you calculate the median survival time, that will be based on the graph or based on the statistical software will give you that period. So this will be your cumulative survival if you are including censoring. If you are not including censoring, if you don't include censoring, then you only take events which has happened. So you will take 1.5, you will take 2.8, you will take 4 weeks, you will take 4.2, and you will take 5 because there were 5 events happened and 5 censored. So you have only taken the 5 events. So if you calculate the taking only event and if you calculate the survival probability, your cumulative survival is 0.5. So you can see that here the survival is more. If you include the censoring, it was 34%. If you don't include censoring, it is 50%. So that's why you can say that there was a overestimation. So if you don't include censoring, that's why it is important to include censored data. So by this analysis, we just want to show you that by including the censoring, you calculate the actual survival time. So depending on the time of censoring, if the censoring happens early, the survival time is underestimated. If censoring happens late, the survival time is overestimated. That's how we will see in the Kaplan-Meier, there is an assumption that the survival time, the pattern and amount of the censoring should be same across the two groups, which we will see in the Kaplan-Meier. I'm not discussing it right now, but the time of censoring is also important. If in the one group censoring is early, in the other group censoring is late, that should not be there. In that case, you have to like interpret the survival curve with caution. Otherwise, we say that the censoring is random in both the group. That means it should be like both in the early, middle, and late in both the group. Or even if it is late, it should be in the both the group. Because if there is a differential pattern of censoring in both the two group, then also there will be difference in the estimation of survival time. So now coming to the life table, which we have started. So life table, it is also known as the actuarial method, because the life insurance companies, they use this. So it estimates the probability of surviving each interval. Because in case of till now, Kaplan-Meier, at a particular time point, we have said that it is you have got a precise estimate. But in case of a life table, you don't have a precise estimate. Rather, you have an interval. So you define the probability of surviving each interval, and you take the censoring within that interval. We will see that. And in this case, since we have discussed that we assume that all those censored people, they were there for half of the risk period. That's why we subtract half of the censored cases. And we assume that censoring was evenly distributed. And on average, each censored person contributes half of the interval of risk time. So that's why in case of a risk set for the life table, basically how you do number at the start of interval minus half of the number censored in that interval. So in this case, in each row you deduct the censored number, unlike the Kaplan-Meier or the previous one which we have seen. For example, this I have taken from the this book. I just forgot the name. Which book we read generally? No, not the Klinbaum. Leon Gottes, yes. I should have written the name because generally I tend to forget. So yes, this is the this is the life table. So you can see here they have given the interval since beginning of the treatment at the end of first year, second year, third year, and fourth year. This is the alive at the beginning of interval, the 375, 197 cases. Died during the interval, these are the numbers. And this is the number of people who have withdrawn from the during that interval. So the effective number of people or the people at risk, it will be like, again, column 2 means alive at the beginning minus withdrawn by 2. So censored by 2. That's how you can see half multiplied by column 4. So like this is 375, 175.5, and this is the risk set. So this is the basis of calculation. So in life table, you will see that in that row, whatever is the censored, you deduct that half of that number from in the same row, unlike the Kaplan-Meier. So that's the difference between the analysis of a survival probability between a Kaplan-Meier and a life table. The previous one, the risk set which we have defined, that is the risk set assumption which we use in the Kaplan-Meier. Because Kaplan-Meier calculates it at exact time point. Whereas in life table, you deduct this from in the same row. So that's why risk set in this case, it will be 175.5. That means you deduct this also, and this number. Since in the beginning you have this number, how this number has come? Like 375 minus, it has deducted this 178, this one. And then here also it calculates the final one. Since here there was no censored, that's why this number and this number is same. 375 and 375 is the same. But in this case, beginning and end it is different because you deduct half of the people who are censored. So that's why the calculation in life table is little different because you deduct half of the people who are censored from your data. Rest is same, like calculating the probability and then calculating the cumulative probability. That is same in this case. Again, this is the same example of interval at risk event censored. So you can see here, since in this case, 5 people got censored here. So that's why what I have done in 97.5, 100 minus 2.5, because I have deducted this 5.2. Similarly, this is the beginning number, and if this is the censored, I have deducted half of this in the adjusted risk set, which is 83. Similarly, if this is 72 in the beginning, and this is the censored is 2, then half of it, that is 1. So I will deduct 72 minus 1 here in the adjusted risk set. So are you getting how we adjust the risk set in the same duration, even the half of the risk set? Because we assume that half of the censored people, because we don't have an exact time point, and that's how the life table is calculated. Have you understood up till this point? Can I see the chat? Yes, can I see? Yes, ma'am. Okay. Thank you. If you have understood up till this point, again, this table for all of you who are not under, I mean, there's a difficulty. This table you get actually. You don't have to calculate it. Just for understanding, I have explained what is the difference in the risk set or the adjusted risk set when you do the calculation using life table or when you do the calculation using the exact time point, which is the Kaplan-Meier survival. Now, there are some assumptions of this life table. So, in the assumption, you assume that there is no temporal change in the effectiveness of treatment or in survivorship over calendar time. So, we will discuss this temporal change in detail when we'll go to the survival and this Kaplan-Meier. But for time being, this temporal change means over the time, means if you are following a particular set of people for, let's say, 5 years. So during that 5 year, you assume that there's no change in the diagnostic modality of the disease, because if there is a change in diagnostic modality, definitely it will impact your left censoring. Because now if some, for example, I'll show you. So this is one assumption. So how you can reduce this temporal change? So it is suggested that you should have the interval as short as possible. That means you should calculate the life. You should not have an interval of 10 years or 5 to 7 years. You can have like 6 months or 1 or 2 months, depending on your study and the unit of measurement. So if you make this interval as short as possible, then you can assume that there is no secular trend or there is no temporal change in the effectiveness of treatment or in survivorship over calendar time. And Will Roger was one person who has defined this, like how if there is a change in diagnosis, it can affect the survival time. And that phenomena is known as the Will Roger's phenomena. Sorry, I'll come to that particular this thing later. So how you can, this was observed that this, again, example I have taken from the Leon goddess. And here you can see the survival experience of two set of so this study was done on pediatric leukemia. So they have seen, like, they have studied this survival analysis. They have done this time to event analysis of pediatric leukemia, and the event defined was death. That after the diagnosis, and they have like split it into black and white, and the number of sample in the white was 194, and in the black it was 27. So number of sample was less in 27, but they have seen that the white, the survival was much better. And if you see, by end of the 4 year, no one survived in case of black. Whereas if you see, the more even by the end of like 5 year or 7, even the survival extended up till 10 years for white children. So that was the difference in survival experience. This was again, so what they did, since it was a long period, so they have followed these children from starting from 1960 to 1975. So the follow period was, if you see this, the follow period was 15 years. So that was a long period. So just to, if you believe that there is a secular trend, you can have the analysis of the 3 different time points. So they have done the analysis of the data from 1960 to 1964, from 1965 to 1969, and from 1970 to 1975. And then they have seen again, like, the survival experience was better for the people of this from the 1917 to 1975 as compared to the people for the children who came in 1960 to 64. So if you split your analysis in different time period, again, which we call it as a stratification, this again will help you to understand if there is a temporal change or not. This was for the black children, and they have also shown that the survival experience from 1960 to 64, it was less, it was 3 years. And for the rest, after 1964, there was a 1 year improved survival. So that was showing that there was some improvement in the treatment and, or the diagnostic this thing. So like I was saying, there is something known as the Will-Rogers phenomena. So what is this Will-Rogers phenomena? So because of some advancement in diagnostic over the time period, there is a improvement. It will appear that there is an improvement in survival statistics, but actually it is not. It is an artificial improvement. Actual patient outcome has not changed, but just because the diagnostic or the advancement in diagnostic accuracy has happened, it will appear that the survival time has changed. For example, and this is known as the stage migration. For example, right now, how we are diagnosing the metastasis. So lung, in case of previously we used to do it in the CT, but now if there is a PET scan. So before a PET scan, only the large visible metastasis was detected, and they used to be classified as a non-metastatic, which is stage 3. But after this PET scan, even the smaller distant metastasis is now being detected. So now we are reclassifying the class 3 to class 4. So what happens that class 3, more severe patients have moved to this stage 4. So now the survival in stage 4, it looks better because it has few patients who were actually stage 3 with better prognosis, and stage 3 survival also improved because here there are only true non-metastatic cases. So that's why you say that the overall survival experience of both these two set of people improved, but actual there was no improvement in survival. So that is known as the Will-Rogers phenomena. So that is just to show you the temporal change. That if there is a temporal change in the diagnostic accuracy, how you can address that? You should have a different survival analysis of that particular time period. The way you have seen in the pediatric leukemia, where they have done the survival analysis from 1960 to 1964, 65 to 70, and then onwards. So am I making sense to all of you? how the change in secular trend can affect your survival outcome, whereas actually it might not happen the case? Okay. So Dr. Ritchie, Dr. Sipra, thank you. So now coming to the article per se. So this article, I think we have shared with all of you. And this article we have created the data set for this article, which is the risk of breastfeeding cessation among low-income women, infant and children. A discrete time survival analysis. And this is the life table, which is describing the breastfeeding experience. And you can see the total number was 309. And they have given the table like number who were breastfeeding at the beginning of the month, number who stopped breastfeeding during the month, and number who censored at the end of the month. Then they have given the hazard function and the survival function. And this they have taken like from birth, then at 1 month, 2 month, 3 month, they have followed them up for 1 year period. Okay, so this is the table which I have taken from that article itself. This is another article. I'm just showing you the example of life table. So they have done the survival analysis using life table. You can see the relapse of subjects using life table. So they have given like this is 1 to 6 month of follow-up period. This is 6 to 12, 12 to 18. They have followed them up for 48 months. That means for 4 years. And this is the withdrawal number. This is the number exposed. And this is the relapse. And this is the survival rate. So relapse, basically, their event was drug abuse relapse. So this is the time until if you see this is since the interval, you don't have the exact time, but this is the event. This 23 is the event. And then they have calculated the survival and the cumulative survival. This table you get actually from the software. This is again the survival analysis. So this they have calculated the 1, 3 and 5 year. This you get in the JAMOVI. It is not a life table. Rather, they calculate it at the 1, 3, 5 and 10 year. So at not a particular time point when the event happened. And this is basically, like I said, that many times patient ask from you regarding the how much by what is the survival probability, or if I'm having this condition, by what time I'm expected to live or maybe to come out of this stage. So for prognosis also, like 1 year, 3 year, 5 year and 10 year, you can have this and then you can show like what is the median survival time depending on this survival probability or the cumulative survival probability of these 1, 3 and 5 year. But there are some limitations. What are some limitations of life table approach? Because it is a fixed time interval and there is assumption that all the events, they are occurring at a uniform rate in the entire duration. But again, it is less accurate in handling the censored data because, we assume that the censored people were there for half of the risk time. So it is not as accurate as Kaplan Meier. It is a less detailed survival estimates. And in case of a life table, you need a large sample size. And again, although you can compare, but there's a difficulty in comparing the survival between groups. So these are some of the limitations of life table. So now I will go to the demonstration. So I hope all of you have downloaded the JAMOVI. So this is, if I will start from beginning. So we have shared the data with all of you. So before the data, I think let's see. We have got few questions for you. So this we have discussed. Now you look into this survival, although I have not explained you the survival curve, but I have explained you the basic of survival, that it is a non-decreasing. So if this is a non-decreasing, what is the median survival time here? Median survival time, I'll explain what is a median survival time. Median survival time is a time when 50% of when the cumulative survival probability becomes 0.5. Then it is a median survival point. That means 50% of the people, they have met with the event. So what is the median survival time here? 2 weeks. Since we have drawn a line also, it is in between like 2 to 3 because it is coming like this. Okay, but yes, you are right. It is less than 2. So 3 and so 50 is coming 3. So it is 3 is here and this 2 will be more than that. If you are saying 2, then I think 2 will not be there. 2 is here. So it is more than that. If you see the line here, it comes here. This. So this is like, you can say it is 3. So median survival time is 3. Now going to another question. So now you have to see the comparison of the two survival curve, group A and group B. So the question is, which group has a better survival prognosis before time T? T star. So if it is T star, which group has a better survival probability? Group A or group B? So in a survival curve, generally the curve which is up, that has got a better survival probability. So group A is a better survival probability if you are considering before time T star. But if I'm considering after time T star, then what is the survival probability? After time T, it is B. So if you consider this after B, then this has got a better survival. B has got a better survival probability. Now, if I ask you like from group A and from group B, which group has got a longer median survival time? So this dash is for the median survival time. So which group has got a median survival time? So if you see, this is the median survival time for group B, and this is for the median survival time for group A. So answer is A, because this is more than this. So the median. So now you have understood how things look in the graph. Regarding if you are comparing the graph which is up or low. So graph which is up, it has got a better survival probability. And the median survival time, what is the median survival time? When the cumulative survival becomes 0.5, or when the 50%, how we say that 50% of the individuals have met with the event. That's the median survival time. So that was with the questions. Now coming to the questions data set. So I'll explain. I'll open the JAMOVI. JAMOVI version you all can download. Those of you, anyone in the group who has not downloaded the JAMOVI, then I will explain. Otherwise, if everyone has the JAMOVI, then I'll skip this part. So can I have any idea whether I should explain or not?
Basically,
so Dr. Shamshad is saying like we have. Okay. So I'm not explaining you how to download JAMOVI, but again, you can download that particular module, which I will show. So this is the demo exercise. I'll open the JAMOVI. So how to open? Since there are many versions of JAMOVI on my PC, but since currently it is JAMOVI 2.6.26. So I will open this JAMOVI because this is the most recent one, solid version. So I have opened the JAMOVI particular file, and then this is the data set. Data set demo updated in June 2025. So you have to use this data set. We have shared the data set with you. So this is the JAMOVI. You can just check the version. It is writing like 2.6.26. Now to open the data, how to open that? Go to new, click on open, and then you can browse from here. But since this, I have already opened this in my data set, so I can click from the left side menu and this data will be opened on my this JAMOVI interface. So those of you who don't have this survival module, you go to this plus sign, click on this plus and go to JAMOVI library. And in JAMOVI library, you type survival. So I will type survival. So when you type survival, you have got these two, death watch and the J survival. So you have and this clinicopath descriptive function of clinicopath research. So all these three, since it is installed in my JAMOVI, so it is coming like this, installed. You can see here. In my PC it is installed, but in your case, it will ask you to install. So install all these three, because these three, there are three modules, but they all have some unique function. So we'll tell that, but you install all these three. Remember Death Watch, which is the first one, J Survival, survival module for clinicopath, that is the second one, and clinicopath descriptive, that is the third one. So now I'll explain these data sets. So this is the problem statement. I'll show the article also. Let me open the article. No, this is the one. No. Risk of breastfeeding cessation. No, this is not the article. Yes, this was the article which we have used to create the data set. You can go through this article. Now I'll come to this. I'll explain the data. So how we explain the data? You can, if you do the double click, this shows you the ID and then keep on scrolling right and right. So I'll move this right. This is the date of delivery. That means date of the delivery of the baby. This date, we have just kept this date to demonstrate. Otherwise, this will not match with the, the total time. So this is the date of delivery, which is there in the format in JAMOVI. This one is your month. This middle one is your day, and this is your year. This is not like a format of day, month, and year. It is month, day, and year. And then it is your date of termination of breastfeeding. This is your date of termination of breastfeeding. And then it is the quarter of year. Means if I divide this 1 year in 3 quarters, if I am assuming that in which quarter it is appearing, if I have to check for the secular trend, I have divided this into the 3 quarter. And then this is the gender of the baby. The male baby is 1 and the female baby is 2. This is your marital status of mother. That means mother is married or divorced or whatever, or mother is single. That means single means they were unmarried. They are single means they are not married. And then coming to the education, the two levels are there: higher and lower education. Education of mother. Then this is feeding education, and that is regarding the number of sessions of the breastfeeding sessions they have received. So that is in the form of a continuous data. And then this is your skin to skin contact. If the skin to skin contact was given or not after the delivery of the baby. This is breastfeeding within 1 hour, no or yes. This is your milk production. That means perception of female regarding the milk production, whether there is enough milk production, little, moderate, more than enough or very little. You can see here if there is a change, very little comes down. So you can change this. I want this very little to go up. So I'll move this very little up and enough down here. So now it is okay. So you can see it is very little, little, moderate, enough, and more than enough. And then it is a gestational age, means age of like birth. That means at 38 week of gestation, the baby was born. Birth weight of the baby in grams. This is your time to event data. That means, how will I say that? 47 days until the termination of breastfeeding. How I will say that? I will read it like 118 days until the termination of breastfeeding, or if I have to say the censoring, 74 days until there was a loss to follow up. Or again the same. How do I say that? Okay, this was the time to event data and the event. So this is my dependent variable. This I was asking you, like in case of a survival analysis, the dependent variable is the time to event, and that is a continuous variable. Yes, of course, this is a categorical variable where you say like whether it is yes or no. Okay. And then we have divided for the sake of this thing again. This is the time to event for demonstration. But again, since in this case, I have the actual time to event. So if you want to express it in the form of a live table, how do you do that? So if you see the JAMOVI, I'll show you. So have you understood the data? I'll just show the question. So this is the, we have shared this PDF document with you. It shows the data description. What is your education level of mother, breastfeeding education, number of sessions of prenatal breastfeeding education. This is skin to skin contact and all birth weight and all time to event. Coming to the additional variables, so we have got date of delivery and date of termination of breastfeeding also, and event time, that is time interval time concept for life table. Now this is how I have to do that life table analysis, and I have to create a life table to estimate the survival for exclusive breastfeeding across gender, marital status, skin to skin contact, and milk production. And so I'll go to this data set and I'll click on this survival. So if you click on this survival, there is, you can say we have downloaded a module which was the death watch. So this is the survival analysis, and then from the clinicopath survival module, we have got these many, like single arm survival. That means it doesn't split in the group, survival for the whole group, no explanatory factor. So I will start explaining. So if you see the life table, that life table option in JAMOVI, you will not find that life table option. So generally it gives you the 1, 3 and 5 year survival. So if I want to calculate the overall survival, how I will go? So click on this single arm survival. I only want the overall survival. So I'll click on that. And then what this time elapsed, you can see here, this is a continuous variable. So I will include this time to event, this one, time to event here. And then outcome is the event. So event I will include here. And then you have to define the event level. So I don't want censored. My event is termination of breastfeeding. So I'll select this termination of breastfeeding from this option. Then I will come down. So now this is the option of advanced elapsed time. That means if you don't have this time to event, you can use the start time and the follow-up date. The date of delivery and date of termination. These two dates, if you enter, it also adds that column to your data. But you don't use both. So since I have got this time, I will show you with this also if you don't have that calculation. So that's why I'm not using. Now, this analysis with multiple outcome, this I'm skipping for now because this happens when in the one person, apart from the one event, there are many other events also. And if you are defined more than one event, then you will use this option. But in this workshop, we are not covering the analysis with multiple outcome. That's why I'm not including this. And then you can come to this plot. And you can write this. This is again, actually, I said that life table is, that option is not there in the JAMOVI. So it calculates the Kaplan-Meier survival curve. Means in that time period, it will give you the probability. And by default, if you see the plot end time, it takes as 60. But you have, yours is like, if I'm calculating it for 6 months, so my end time will be 180 days and my time interval is, let's say, 30 days. And I want like censored data also. And I want survival table also. So survival table, I will change this to like 30 days, 60 days, 90 days. I am taking the 1 month interval. 120 days, 150 days, and 180 days. So you see that it gives you a survival table here. 1, 3, it gives you like 1, 3, and 5 years survival. It writes actually 1, 3, and 5, but actually you are changing it in days. That's the default this thing. And again, time, if you see, it is writing in months. So because mine is in days. So you can change that to day. And to change that, I think if you have to change the dates here. So click this, change this to days. And then again uncheck that. Then this time gets changed to days. You can see here, this time is now days. And then you can have a risk table also. You can have a, if you want to, in the plot, if you want to have 95% CI, then also you can have that. So it gives you the survival plot. It gives you the time at 30, what was the number of risk, total number of event, and what was the survival. So you can see the survival was decreasing with time. So that's what we have learned, that it is a non-increasing. So at the end of 6 months, how will you say? Only 9% of the female or 9% of the children were, continued the breastfeeding. There was no cessation because that's the survival probability. That means past 180 days, what percentage of the study subjects survived? So we say 9% survived past 180 days. That means beyond 180 days, only 9% of the mothers, they were exclusively breast feeding. Yes, Namratam, they are exclusively breastfeeding. And this gives you the lower and upper 95% confidence interval. To change the this thing, and this is again, if you see, it is based on the Kaplan-Meier survival. This is not the life table one. This is the Kaplan-Meier. Because I said, like, generally life table, it is not used very commonly these days. So that's why in JAMOVI we could not find that option. And here I have changed the dates with this, like this. You click on this advanced elapsed time option. Click on this using dates to calculate survival time. Come down, and from here you can see it is writing the days. And you can see here it is year, month, and day. It is like that. But they have some other this thing also. No, I'm not changing. I'm just seeing it because we have to. So this was your, this is how we change it. And it writes also here. If you see, it writes like the estimated probability of surviving beyond 30 months was 99%. At this time point, there were 200 subjects still at risk and 2 events had occurred in this group. So this is the description. You can write this also. By, of course, not these many intervals, but the interpretation, you can take help of this write-up also. Like at the end, it is writing, at this time point, there were 13 subjects still at risk and 4 events occurred. So the estimated probability of surviving beyond 180 months was 8.5%. This one. So this was because it is in whole number, that's why it is not giving you exact percentage. It took it as a 9%. So these are the options. And survival table I have shown you, cut point you have to show. And then if you wish to have a person time analysis, you can click that person time analysis also. Here also you define the matrix like, you know the person time, you calculate the incident rate using the person time. So in the numerator, you take the number of events happened, and in denominator, you take the total person time. So here also you can divide it like 30, 60, 90, 120, 150, and 180. And rate multiplier is 100. So if you see, it is giving you the in time interval, what is the overall incident rate, and it gives you the total overall incident rate is 0.89 per 100 days. So on the basis of person time, it calculates the incident rate also of incidence of cessation of breastfeeding. So this also you can use. So this is one. So Abhi, for now, you can see with this option, or you can go to here, that median survival line that doesn't appear. So if you go to this survival analysis death watch, but with this survival analysis, you don't get the table. So I think this is the better option of using the one option, this one arm survival. So if it is okay, you can go to the breakout room. Any question before we go to the breakout room and practice on the data set? So Anand, are you there?
Yes, ma'am.
So you can make 3 breakout room. I think Dr. Haripriya, Dr. Parvati,